Hello and welcome to more problems from the book Orbital Mechanics for Engineering Students by Howard D. Curtis. I'm on to problem 1.5. Problem 1.5 gives us a particle with a position, and it wants us to find out a lot of properties of this particle at time equals 3. I'm going to try to get everything on one page, and I'm going to start with the function for its position vector as given in the question, which is sine 3t plus cos tj plus sine 2t k. And the first thing we're going to do with that, because the question involves it, is we're going to get the derivative of that. And the derivative of distance is velocity. So vector v of t is 3 cos 3 of t, because the derivative of sine is cos. And we bring out the 3. And then the derivative of cos is sine, so we have minus sine t j, and again the derivative of sine is cos, and we bring out the 2 t k. And then we're going to do another derivative to get the acceleration, because again that's what we need in this question. So the derivative of cos is minus sine, so that becomes minus 9 sine 3ti, and minus cos tj, and then minus 4 sine 2tk. Those are 3 equations of motion that are included, that are involved in this question. So part A is asking for the velocity at time equals 3. So v3 equals, you plug in those numbers, you get minus 2.733i minus 0.1411j plus 1.92k. And then B asks for the speed, which is just the magnitude of that. So we'll just say v3. And if you do the magnitude equation, square it and sum it, and then take the square root, you get 3.343 meters per second. And then part C is asking for the unit tangent vector, and that is straightforward as well, because that is just is equal to the vector v divided by its magnitude, which is just divide that through with that, and you get minus 0.8175i minus 0.0422j plus 0.574k. Then part D is asking for the angles of the vector v with the x, y, and z axis, and that's pretty straightforward as well. You just have to take the dot product with the axis. So D, we have the vector v dot product with the y-axis, which is a unit vector, equals the magnitude of v times the magnitude of I times cos the angle that we're after, which in this case would be x. And then that's the same for all of them. And this is the y direction. That's a j. Cos theta y and vector v dot k equals v k cos theta z. And if you solve for, so do the dot product on these, solve for theta x, you will get theta x equals 144.84 degrees, theta y equals 92.42 degrees, and theta z equals 54.95 degrees. Obviously I've already worked these out, so then part E is asking for the acceleration A in Cartesian coordinates, so that is just A of 3, which is minus, you put that into your acceleration equation, you'll get minus 3.709I plus 0.99 J plus 1.118K. And then part F is asking for the unit binormal vector. Yeah, and there is an equation for this, which is essentially just taking the orthogonal vector to the velocity and the acceleration, which are both on the same plane anyway. So then the vector off that will be coming out of the plane perpendicular, which is what we want. So that equation is, so that's the vector cross product, the acceleration, and we want the unit vector, so we just take the magnitude of that as well, and that is equal to the cross product. So the cross product is as such, so vyaz, vz, ay minus vx, az minus vz, ax plus vx ay minus vy ax z x xy yx, and then that's going to be divided by the same thing, but the magnitude, I'm not going to write it all out again. And we're going to compute the top row first, which is down here, which equals, if you multiply all that out from these values, so you can get your vector values here and your acceleration values here, chuck those in, you should get 2.059I minus 4.0658J minus 3.229K. That is, and then that is, and we take the magnitude of that, equals 5.585, and then we divide that through, and our unit vector, binomial unit vector, is minus 0.3687I minus 0.728J j minus 0.578 k. And then it wants us to get the unit normal vector as well. So that's part E, that's part F. Now we're on to part G. So the unit normal vector is equal to the binormal vector cross product with the tangent vector. And we have that here, the binormal vector, and we have the tangent vector here. We plug them into the cross product formula. We should get minus 0.4423i plus 0.6841j minus 0.57958k. And then the next part is H, which is looking for the angles between the acceleration vector and the axes. For that, we're going to need the magnitude of acceleration. All of this is at 3 seconds. The whole question is at 3 seconds. The magnitude of acceleration, we have the acceleration here. So we just get the magnitude of that, square all the values of them together, take the square root to get 3.998 meters per second squared. And then we're going to do the same equations that we had before for the angles, the vectors, the velocities, sorry. But we're going to do it just a little bit different. So the angle for acceleration x equals cos inverse a of x divided by a. The angle for y equals cos inverse a of y a. And the angle for z equals cos inverse a of z divided by a. And that is just that equation there, you know, just done out simpler and things cancelled out, like so. And we get 158 degrees here. Here we get 75.66 degrees. And here we get 73.76 degrees. The next part is part I. That is looking for the tangential component of acceleration, which we can get by projecting the acceleration vector onto our unit vector t. And you can project just by doing the dot product. Get the magnitude, so the magnitude of the tangential acceleration. You can do that by projecting the acceleration onto the unit vector. This is also the derivative of the magnitude of velocity, and you can work that out. There is a derivation for that which shows it to be true. But anyway, if we multiply the acceleration, which we have here, dot product with the unit vector t that we have up here, you should get 3.321 minus 0.04178 plus 0.6417, which equals 3.63 meters per second squared. And then the next part, J, wants us to get the normal acceleration, which again is the same, we're just projecting it onto the normal unit vector of the normal, and that will give 1.6405 plus 0.6773 minus 0.648, which equals 1.67 meters per second squared. At this point, I would probably actually confirm this by recombining this to get the acceleration using the formula for that, which is A equals AT unit vector T plus AN unit vector A, just to confirm that we do in fact get back to our original acceleration values, but I'm not going to do that right now. I'm pretty sure this is correct. The next part of the question wants us to get the radius of curvature of the path of P. So this is essentially just saying that if our particle is going like this, right, there's a point somewhere here that is curving around at that instance. So, and the formula to get that value, which I think is pronounced rho, is the v squared magnitude of velocity squared divided by the magnitude of the normal, which equals 6.69 meters. And then part L is just the last bit. It's just asking for the center of the curvature of the path. So to get that, we're going to take this point here, P, and this is 6.69 meters. And we also know that this is our normal vector, so our unit normal vector. You know, it goes out there. It's along that line. That is, so it's going to be P plus rho times our unit vector. So that's the point, and then we're adding on a vector to get back to the center. And if you plug in your 6.69, well, the point is we plug 3 into our distance formula, our position formula, sorry, we will get where have I put that? Yeah, 0.412 I minus 0.99 J minus 0.279. So that's P, right? And then if we work out the rest of it, we get minus 2.547 I plus 3.59 J minus 4.156 K. So that is it. That is the whole question complete. All of this information is on how to do this is in the chapter. You can go back and look at them. But there's nothing particularly unusual in here after you go through it. So that's that 1.5. Thank you very much.